Hi everyone, and welcome to the first of 4 videos going through some past exam questions on ligand substitution and also precipitation reactions of transition metals. The first question here, we got a few sort of little questions to start us off. So it says it refers to chemistry of the D block elements in period 4. For each statement below, select the symbols of the correct elements. So which is the element that has atoms containing 6 electrons in the 3D subshell? This is nice and easy. We just need to look on your periodic table. D subshell, 6 across. So 1, 2, 3, 4, 5, 6. That's going to be iron. Okay, that's as simple as that. Okay, so that's a nice easy one. The second one, it says 2 elements that have atoms with 2 unpaired d electrons. Okay, well the first one of those is going to be easy. That's just going to be the element that has 2 electrons in the d subshell. Okay, because they don't pair up unless they have to. Okay, they'd go 1 electron into each orbital. If we think about doing electrons in boxes here, just for a second, this is how we'd work this out. We can have our 5 d orbitals, aren't we? So we're looking for ones with 2 unpaired d electrons. So we'd have 1 electron there, 1 electron there. So we want the element that's got 2 electrons in a d subshell. So that's going to be titanium. Okay. And then to get the other one that's got 2 unpaired d electrons, if we kept putting electrons in here, we're going to keep putting them in separate orbitals, aren't we? So that's 5. And then we're going to start pairing them up again. So 6, that's got 4 unpaired d electrons. 7's got 3. 8 would be the other one that's got 2 unpaired d electrons. So we're looking for the 8th element along. So 1, 2, 3, 4, 5, 6, 7, 8. So it should be nickel is the other one. Part 3 is a question that's not in the specification anymore, so we're going to ignore that one. Part 4, element X that forms an oxide with the formula X3O4 with a molar mass of 228.7. Okay, so if it's X3O4, so oxygen O4 is going to be 16 for oxygen times 4, which is 64. So 228.7 minus 64. Take off the 4 oxygens, that'll leave us with X3. 228.7, take away 64 is 164.7. Right, and then we need to divide that by 3. And we get 54.9. So element X is going to have a mass of 54.9. Which looking here is manganese. There we go. So that's hopefully not too bad. Part 5, element that has atoms with an average mass of 8.64 times 10 to the minus 23 grams. This is a bit of a strange question. So we go, right, the mass of an atom, but sort of as soon as you see a number like the 10 to the minus 20, this is making me think of Avogadro's number. Okay. As soon as I see 10 to the minus 23. If that's the average mass of one atom, then if we want to know the average, we want to know the mass of 1 mole of atom. So if we times this by Avogadro's number, so if we do 8.64 times 10 to the minus 23 times by 6.02 times 10 to the power of 23, that's going to give us the mass of 1 mole of atoms, isn't it? So hopefully you can see that the 10 to the minus 23, 10 to the 23 will cancel out. So I'm not going to bother doing that. I'm just going to multiply the other bits. 8.64 times 6.02 is 52.01. So we're looking for the element that's got an atomic mass of 52, essentially. So that is going to be chromium. Okay. That's kind of a giveaway. Anyway, you see a number that looks kind of horrible like that, you're going to want to use Avogadro's number. So those are all just some sort of transition metal-y type questions. Now we're getting into a bit of a ligand substitution going on here. So the flowchart below shows 3 reactions of the complex ion CuH2O6 2+. So this is one that we do need to know about. Okay, copper. In the boxes, write down the formula of the species formed. Right. So this copper hexaaqua complex here is this pale blue solution. And if we add some ammonia to it, we end up with a deep blue solution. What's happening here is, remember, if you add a little bit of ammonia, you're going to end up making a precipitate, actually the same precipitate as you make here. Let's do this first, actually. If we're making a precipitate, this is going to make the precipitate of the hydroxide, right? So this is going to make, it's copper 2 plus, isn't it? So it's going to make copper 2 hydroxide as the precipitate. When we're adding sodium hydroxide, we'd actually get the same precipitate from the ammonia, because the ammonia would accept a proton from water, and that would create the OH minus ions that would then create this precipitate. But if we keep adding the ammonia, that precipitate would then dissolve and give us this deep blue solution, and that's where we've actually done a ligand substitution, where the ammonia is now going to be a ligand. But this is an annoying one. Copper is one that you do have to remember. We don't substitute all of these ligands. Okay, this deep blue solution has 4 ammonia ligands in it, and it still has 2 water ligands. And it's still going to have a 2 plus charge because all these ligands are neutral. Okay, and that is just one that you need to remember, unfortunately. It's beyond the scope of the course to explain why we don't replace all 6 of those ligands. That's not something you'll be asked. So you're just going to have to take their word for it on that one, that is the product you get, and you need to learn that one. And then finally, this is the other ligand substitution reaction of copper that we need to know about. If we're adding HCl, we're going to add chlorine. Chlorine is going to substitute for the H2O as the ligands. And again, here we only get 4 ligands going on. This one we can explain. It's relatively simple. It's just that the chloride ligand is too big to physically fit 6 ligands around it. So that's why you only get 4 substituting on. At least there's, you can try and remember this. You go, oh, there's 4 chlorines go on here and there's 4 ammonias go on there. Don't forget about those 2 waters still there. But hopefully that kind of helps you remember it a little bit. And there's a bit of consistency of sort of 4 ligands with the copper. But we need to think about the charge here. These chloride ligands are chloride ions, so they've got a negative charge. So if there's 4 of those, that's 4 minus, and it was 2 plus to start with. So it's now going to have a charge of 2 minus. Okay, so don't forget to think about the charge, okay, because the charge is the combination of the charge of the transition metal and the charge of the ligands. Okay, so that's kind of a nice summary of all the ligand substitution reactions of copper that you need to know about, and the precipitation reaction. Right, we then have this question which talks about nickel. Now this is not something that you're expected to know about. You need to know about copper and chromium. So you're not expected to know about nickel, but they've given you so much information here that you can work it out from the information they've given you. That's the kind of question that we're going for here. So nickel 2 sulfate, you dissolve it in water, you get a green solution. You get this nickel hexaaqua thing, and this isn't not stuff you're supposed to know. They then react separate portions of it as outlined below. Concentrated hydrochloric acid is added to it until there's no further change, and you get a lime green colour, and you get a 4 coordinate complex ion. Okay, now I'm going to do this one at a time, right? What this is asking us for is what is the formulas of A, B, and C here. So I'm just going to go and do this straight away because we've just seen it from here, right? We've just seen copper when it reacted with HCl. We got a 4 coordinate complex with the chloride ions. And nickel here is just going to be doing the same thing. Okay, so A here is going to be nickel with 4 chlorine ligands. And again, we need to think about the charge. Again, this was 2 plus. There'd be 4 chloride ligands that would each have a negative charge. So again, it's going to be a 2 minus charge. Okay, so there's a nice bit of sort of consistency there. That's what I mean by you're not supposed to know that, but you've seen something similar. You can work it out from what you've seen before and from what information they've given you. Aqueous sodium hydroxide is added, and you get a pale green precipitate. And so again, there's a similarity here, right? With this copper complex, you add sodium hydroxide, you get a pale blue precipitate. And it's copper 2 hydroxide. This nickel, this was a green solution. You add sodium hydroxide, you get a pale green precipitate. So this is going to be the same thing. This is going to be a precipitate of nickel 2 hydroxide. Okay. So there are sort of themes. They're wanting you to apply the knowledge that you know about copper to this example. Concentrated aqueous ammonia is added until there's no further change. So the solution then turns a violet colour and has a complex ion C. Okay, so this is presumably going to be a ligand substitution reaction. So again, it's going to be similar here. We're adding ammonia. We're going to end up with something like this. But the question is, are we going to do the same thing that we've done with copper, where we only get 4 ammonias being substituted? Or are we going to substitute all 6? Again, this is nickel. You're not expected to know about nickel. You are expected to know that copper does this. There's no way for you to know whether nickel does that or whether it substitutes all 6. Okay, and that's why they've given you the molar mass here, so we can work this out. Okay, you're not expected to know this. So it was 160.7. If we take away the molar mass of nickel itself, so nickel is 58.7, so if we take that off, then that leaves us with 102. The NH3 ligand is going to be 14 plus 3, isn't it? It's 17 grams per mole. Put this on there as well. So then if we now divide this, if we do 102 divided by 17, let's see if this comes out as a whole number. Yeah, it comes out as exactly 6. There you go. So that is telling us that we have got 6 of those ammonia ligands. It's substituted all 6 of them. Okay. If there were some ammonias and some waters, then this would come out as 6 point. Well, no, it wouldn't come out as not a whole number, because obviously the water ligand has a mass of 18. So if that didn't come out as a whole number, that would show us that there must be some combination of both. But that's telling us there must be 6 ammonia ligands. So therefore, this must be nickel with 6 ammonia ligands on it. And the ammonia ligand is neutral, it's not got a charge. And this was nickel 2 plus, wasn't it, from up here? So it's still going to be a 2 plus charge here. Okay. It then says write an equation for the formation of C, so this thing, from this one. So nickel H2O6. And we're just swapping the 6 waters for the 6 ammonias, right? So we're going to add 6 ammonia, and we're going to end up with nickel no, we're not. Idiot. We're going to end up with nickel NH3, 6 plus 6H2O. Okay, it's just a straight substitution, right? That's the whole point. It's ligand substitution. So hopefully that's not too bad, right? But we do need to be careful because there was this question that we've missed out. So let's just go back and finish this off. I was just kind of working my way down here. So now it says draw a 3D diagram for the nickel H2O6 ion and show a value for the bond angles. So this is nice and straightforward, hopefully. If you've watched, especially if you watched the videos on transition metal complexes earlier, if we've got 6 ligands, this is going to be octahedral geometry, isn't it? And octahedral geometry always looks the same. We're going to have our central ion. We have 2 ligands above and below. We have 2 ligands that go back into the plane of the paper that we show with dash bonds. And we have 2 that come out of the plane of the paper that we show with the wedges. And it's H2O ligands. Again, I would be careful showing the connectivity here. That remember, a ligand is forming a coordinate bond by donating a lone pair. That lone pair is going to come from the oxygen, isn't it? So let's draw these so that we can see that they're bonded from the oxygen. So I'm going to write these 2 backwards. Let's put this on, so it's through the oxygen. These are through the oxygen. Okay, this whole complex has a charge of 2 plus. And it said it wanted a value for the bond angle. So that bond angle is 90 degrees, isn't it, in an octahedral complex.